Hello, this is Graham Neubig, and welcome back to CS 11747 Neural Networks for NLP. This time I'll be talking about adversarial methods. So adversarial methods are a fairly wide variety of methods where the basic idea is that we have a model and then we also have an adversary, and they work together in tandem to learn. And the most kind of stereotypical version of this are generative adversarial networks. And in generative adversarial networks, basically the model generates output, for example, text, and the adversary attempts to detect whether a text is generated or genuine in order to help the model learn better. Adversarial feature learning is another variety where the model generates features, for example, through an encoder, and the adversary tries to distinguish features of different types in order to move them together or spread them farther apart. Adversarial robustness, on the other hand, the adversary tries to perturb the inputs to cause the model to fail. And in the case of adversarial training, the model may be trained to be robust to these perturbations. So you can see that all three of these things are kind of different in flavor, but they're all the same in that they have a model and an adversary. And I'm going to go through some examples of each of these types of methods. So first, let's try generative adversarial networks. So generative models overall are trying to model a data distribution P of X or a conditional data distribution P of Y given X or P of X given Y. And latent variable models introduce another variable Z and model P of X given the integral or sum over all of these latent variables. So a perfect generative model would be able to evaluate the likelihood, for example, perplexity in language modeling. Also generate samples, so generate a sample randomly from a P of X or conditioned on some other information. And it could also infer latent attributes. So if we have a latent variable Z, it should be able to infer the C given X, such as inferring a topic of a sentence in topic models. So no generative model is perfect. So for example, we have talked a lot about different non-latent generative models, like just regular language models using LSTMs or transformers, whatever. And with respect to, there's also variational autoencoders, which we'll be talking about in next class. And there's generative adversarial networks, which we'll be talking about in this class. And so basically the non-latent ones tend to be good at likelihood calculation. VAEs get decent likelihood, but may not be as good as regular non-latent models. And GANs are kind of fundamentally not maximum likelihood estimation models, and thus are not super great at calculating perplexity or likelihood. However, on the other hand, when you're doing generation, particularly for things like images, GANs really shine, and there's a reason for this that I'll be talking about soon. And for inference of latent variables, VAEs tend to be a little bit more conducive to this, although GANs can be used for this as well. So basically, long story short, GANs give a good tool to kind of generate very natural looking text and can kind of smooth out some of the issues that other methods for generation can have. So this is just an example of a maximum likelihood estimation trained model versus a GAN trained model. And basically, if we look at the real one on the left and the MLE one in the middle, basically we can see that the real output is rather sharp. However, the MLE one is quite fuzzy, so the overall shape is not bad, but it's kind of blurring out the ear, and the eyes are not sharp, etc. On the other hand, if we look at the adversarial output, it's still a little bit sketchy because this was an image from 2015, but you can see at least it's very sharp in the way it is created. And the reason for this, and this is not just for images, it's for text as well, is maximum likelihood estimation essentially is trying to find outputs that are kind of safe and will maximize the likelihood. Whereas, so, it wouldn't want to make any hard decisions that would cause it to rule out any plausible outputs. So because of this, generating a fuzzy output or generating a probability distribution leading to a fuzzy output is not necessarily a bad idea. GANs, on the other hand, are trying to generate images to fool a discriminator or an adversary. And if an adversary saw that all the images were fuzzy, it would just be able to say, okay, this is a fuzzy image, so this is fake. This is a real a sharp image, so it's real. So the GAN objective kind of encourages the model to be more bold and make some decisions here. So going into the basic paradigm, we have two models, a generator and a discriminator, which functions as an adversary. And the discriminator, given an image, tries to tell whether it's real or not. So it calculates the probability that the image is real. On the other hand, the generator tries to generate an image or text or whatever other kind of output that fools the discriminator into answering real. And so the desired result at convergence is that the generator can generate perfect images and the discriminator cannot tell the difference between them. The training method is basically for the real images, we sample a mini batch of real images from the database that we have. And then for the fake images generated by the generator, we sample latent variable z according to, for example, a Gaussian distribution. We convert these with a generator into fake inputs or outputs. And then with the discriminator tries to predict real or fake. And the discriminator loss is higher if it fails predictions. And this backpropagate, okay. Then we have the generator loss, which is higher if the discriminator is able to correctly identify fake images. So basically the generator is trying to generate images that cause the discriminator to fail. And the gradient backprops like this. So basically the discriminator loss backprops into the parameters of the discriminator, and the generator loss backprops into the parameters of the generator. So the good thing about this is basically these models are now competing against each other, where the discriminator tries harder and harder to identify images that look fake, and the generator tries harder and harder to fool this discriminator. So in equations, basically what this looks like is we have the discriminator loss function, which is an expectation over the data, where we encourage it to predict real for real data. And we have the expectation over the latent variables, where we encourage it to predict fake for fake data. And then the generator loss function, we try to make the generated data less fake. So basically, we make the generator loss function the opposite of the discriminator loss function. We just flip it in the opposite direction. And this is called a zero-sum loss, because now it means the loss will be zero when you add the two models' loss together. And we could also do something that tries to make the generated data more real. And this is called the heuristic non-saturating loss, because basically what it does is it only takes the loss over the generated outputs and tries to calculate the loss over here. So it's only taking the second part. So the reason why this the second loss is maybe preferable is basically, if we look here, the loss value, if the discriminator is very good, the discriminator loss will be near zero. So like, let's say right at the very beginning of training, the generator is kind of not very good at all. this loss will be near zero, and the loss will kind of saturate and give very few gradients. So we might converge to a poor local minimum where basically the discriminator loss is bad and we never improve, or the discriminator loss is good, the generator loss is bad, but we never improve. So what this does is this ensures that the generator losses continues to be poor if the discriminator is doing a very good job. So this kind of makes sure that the generator will keep training in these situations. So another way to interpret this is basically distribution matching. And this is particularly important when we're also talking about other varieties of training as well, other varieties of adversarial methods as well. So basically the process is that we have a distribution P of z, and this P of z is the distribution over latent variables, where P of z can be any distribution that we wish. And then we have a transformation from this P of z to P of x, where this can be any arbitrary deterministic function that transforms between these two distributions. And as a result, x is a random variable with an implicit distribution P of x, which is decided by both P of z and f. And the process can produce any complicated distribution P of x with any P of z and a powerful enough f. So another way to think about this is P of z might just be a Gaussian, for example, over a multivariate Gaussian over latent variables of a vector of latent continuous variables. But then we run it through a neural network that does a very powerful transformation and converts this instead into, all of the images in the world or all of the text in the world or something like this. So I think this is a very interesting way of thinking about things, and it's good for, to think about this conceptually, because it demonstrates why these latent variable models are able to, even if we have a kind of simple latent variable like a Gaussian, we can nonetheless generate, a very complicated distribution like that of all natural images or text. So in pseudocode, how do we express this? So x real is sampled from the training data. Z is sampled from the distribution over z. We generate x fake. We calculate the discriminator for both of these. So these are the probabilities that x real is real, x fake is real. And then we calculate the training objective for D and the training objective for G using the non-saturating loss. So it's really, about this simple. So why are GANs good? Basically, the discriminator is a learned metric parameterized by powerful neural networks, and it can easily pick up on any kind of discrepancy between the inputs and outputs, including like global inconsistency or other things like this. So the generator has fine-grained signals according to the gradient to inform it and on what and how to improve. So just to give an example, going back to the example of blurriness in images, detecting whether an image is blurry or not is very, very simple for a discriminator. And because how the discriminator distinguished between a blurry or non-blurry image is backpropped into directly into a GAN or into the generator, this also tells the generator what exactly it needs to be improving to hurt the discriminator performance. However, there are a number of problems in GAN training. So they're great conceptually, but training is notoriously difficult. And there are known problems on convergence and stability. There's solutions to this like the Wasserstein GAN or gradient-based regularization. There's also things like mode collapse. And so what mode collapse is basically the model learns not to generate kind of random, nice-looking things, but rather exactly the training examples that appear in the training data. And if that's the case, it's not a very good generative model because essentially it will overfit and only generate these things. So there's other methods like mini-batch discrimination where you try to discriminate over the entire mini-batch instead of a single example, or unrolled gans, etc. Another issue is overconfident discriminators. So the discriminator very quickly becomes overconfident, and there's other things like one-sided label smoothing. So I'm not going to go into all of the details here. I think the most important thing is that you just know that there are problems in GAN training, but there's lots of solutions to them, and the most recent GAN literature can kind of give you a good idea of the tricks that need to be used to fix these problems. Okay, so up until now I was talking a lot about images, which is also where GANs have been applied most profusely, but they've also been applied to text. So for example, they've been applied to language generation, machine translation, dialogue generation. Notably, a lot of these are around 2017 because that's when GANs kind of became very popular. But there's also a number of problems when you apply GANs directly to text generation. So for text, for image generation, the discriminator, you can backprop all the way through it because it's taking in continuous image variables and making decisions over these variables. But in the case of text, this X fake here is a discrete textual sequence, which means that it's not easy to backprop through this because we're essentially using discrete variables. So one solution for how to fix this problem is to use learning methods for latent variables. And we've talked a bit about some of these, for example, using policy gradient or reinforcement learning, like we talked about in the previous class on structured prediction. And there's also other tricks like reparameterization tricks for latent variables. And because I know we haven't covered these extensively in class, just to give the basic idea of the way these work, when we calculate discrete latent variables, we have to make decisions using an argmax function. So basically, what we do is instead of making a discrete decision with the argmax function, where we take in inputs and we output a one-hot vector, we instead output kind of a smoothed one-hot vector that is nonetheless differentiable. So I'm not going to go into a lot of details here just in the interest of time, but if you're interested, there are other options compared to reinforcement learning-based methods. So in terms of discriminators for sequences, basically this is a sequence classification task, and we want to decide whether a particular generated output is a true output or a fake output. And it was common to use CNNs as discriminators either on sentences or pairs of sentences. Now you could certainly use something like BERT as well to make these discrimination decisions. However, I do think there's some benefit in knowing about the architectures that people use because, like, for example, if you want to compare the source sentence and the target sentence with respect to whether it's true or not, the association between individual pieces of the source sentence and target sentence are rather important. So instead of just throwing everything into one big CNN or attention-based model, you might also want to consider things that kind of look pairwise at the source sentence and the target sentence. And this is one example that uses a three-dimensional convolution to help you do this. So it basically forms the source sentence and the target sentence into a three-dimensional tensor and does convolution and pooling over them to try to make the final prediction. So this is something you might also consider if you want to work with adversarial methods for text. So I think fundamentally the idea of GANs is very intuitive and attractive, but GANs for text are also hard to train, and they're even harder to train than GANs for images. So it kind of there's a lot of things that go into training the models, whether they work. So for example, the type of discriminator you use might be important. The strength of the discriminator and the learning rate might be important. So if you get the parameters just right, you can train it well. If you don't get the parameters right, it becomes more difficult. So this is something to be aware of and to look back at the literature if you're going to be using these methods. Here's another example with the learning rate for the generator versus the discriminator and learning rate for the discriminator. So you can see these are relatively sensitive to some hyperparameters. So one type of stabilization trick that is rather important, particularly for text, is to assign rewards for specific actions in the generation output. So getting a reward at the end of the sentence causes a credit assignment problem where you don't know particularly which output caused you to be penalized. And as I mentioned before, this is a really big benefit of GANs for images, for example, because you can backprop all the way through the discrimination process to automatically get feedback to the generator about what part was a problem. So in text, one solution is to assign rewards for partial sequences. So you gradually step through the sentence, and the point where you start getting a signal that it's fake. So like, let's say we put this is a fake. This is the place where the discriminator starts to give a feedback. So you can assign a reward for partial sequences and particularly penalize the actions that cause this partial reward. There's other stabilization tricks, and these are kind of generally stabilization tricks for reinforcement learning methods as well, like performing multiple rollouts. So this is one example of adversarial methods for text, where basically it calculates up to a particular state, then does a bunch of actions, and a continued search before you finally get the reward. So as I mentioned, there's one issue with doing this over discrete sequences, which is that you can't backprop through the results. So there's actually some other options that are fully differentiable and nonetheless allow you to apply GANs to text generation tasks. So this particular example is discrimination over softmax results. So you have a discriminator over not the final output, but rather the probability of each action. And because this is still a probability distribution, you haven't yet done the argmax to get the final output. If you apply the adversary here, then that allows you to backprop all the way back. Okay, so this is an example for GANs. So now I'd like to move on to the second type of adversarial method, adversarial feature learning. So if we think of adversaries over features versus adversaries over outputs, generative adversarial networks are basically putting the adversary over this Y here, whereas adversarial feature learning is putting the adversary over this H. And so the hidden features H are the things that we're discriminating over. And there's a number of reasons why we'd want to do this. For example, non-generative tasks. So if we have just text classification, there might be times when we'd like the features to have a particular trait. So we run this sort of distribution matching over the features to encourage this trait. And another reason is that, as I mentioned before, discrete outputs are hard to optimize over. So we can use continuous features instead. So one example of why we might want to apply an adversary over features is to learn domain invariant representations. So we might have text from a number of different domains, such as movies or books or household goods or things like this, and want to predict labels over these, like let's say sentiment labels of reviews. However, the wording that people would use in all of these different domains would be very different. So that might cause problems if we, for example, want to try to share information between these different domains. So basically the way adversarial feature learning works in this case is we have a loss over our class labels for to train the text classifier, for example. But then we also have a domain classifier where we have a reversed loss, a gradient reversal layer here, that essentially tries to fool the discriminator that tries to discriminate over domains. So what this means essentially is we try to create features that are useful for solving the target task of text classification, for example. And then we have, but we try to prevent the features from being useful for discriminating the domain. And so what this is doing is it's essentially matching the distribution of the features across the different domains while still allowing them to be able to solve the task, which makes it seem like these will be more transferable across domains and allow for high accuracy in one domain when they're trained on another domain. These can be applied in any different way, not just necessarily domains, but they could also be applied to, for example, synthetic to real domain adaptations. So if we have synthetically generated data or data augmented data, we could use a domain discriminator, or like older data that doesn't match the current distribution we'd like to adapt to. So this paper by Kim et al. Demonstrates how this can be done as well. Another example, because in language we have many different languages, is learning language invariant representations. So for example, we might have a sentiment classifier that's trained on English data, where we have a language discriminator over English and Chinese. And we try to force the representations closer together so that the English classifier is easy to transfer to Chinese data. And it can also be used for other tasks like multilingual translation. Another idea is adversarial multitask learning. So if we want to do some features, if we want to do multitask learning, when we're doing multiple tasks, the tasks are inherently different, so the features that need to be used are similar in some cases, but also different in other cases. So we want some features in a shared space across tasks and others separate. So this is something called a shared private model, where we basically have some private features that are used only for a particular task, task A or task B, and then we also have some shared features that are used for both. And then what you can do is you can use adversarial learning to ensure that the shared features follow similar distributions, but the private features follow different distributions. And you can use an adversarial classifier to do this. And this is a paper by Peng Fei, one of the co-instructors of the class, so you can feel free to ask him more questions about this. Another example is something called professor forcing. So this is a little bit like a generative adversarial network. But basically the idea is that we generate an output sequence according to the model, but train the discriminator on hidden states. So basically we have a sampled or true output sequence here, and then we have an adversary on the hidden states. And what this tries to do is this tries to essentially force the hidden states to be similar between the adversaries and the between the generated and the fake results. So this is kind of yet another way to encourage generated outputs and fake outputs to be similar. And adversaries can also be used for things regarding unsupervised distribution matching. So as I mentioned before, distribution matching is important, or is one interpretation of these adversarial methods. But there's a number of applications to NLP where you would want to do this sort of unsupervised distribution matching. So one example is unsupervised style transfer for text. So we would like to transfer sentences with one style and generate sentences in another style. So for example, decipherment is where you would want to translate ciphered sentences to natural sentences. Transfer sentences with positive sentiment to negative sentiment. Do word reordering. And basically the way the model works is you have a generator that tries to generate in one style or another style, but you have a discriminator that tries to discriminate between the two styles. So you essentially take in a original sentence and transfer it to a new style and try to train a discriminator so it can't discriminate whether the sentence is an original sentence in that style or a automatically generated sentence in that style. It can also be used for alignment of embeddings in different spaces. So let's say we have two word embedding spaces A in different languages, and we want to get them so, like, let's say we have an English embedding space and a Spanish embedding space. And in the end, we would like to get them to align, the two embedding spaces to align. And this is useful for like cross-lingual transfer applications or inducing word dictionaries from word embeddings or other multilingual applications like this. But basically what we do is we define a function such as an orthogonal transform to map between the embedding spaces. And then we train a discriminator that tries to distinguish between the two, whether an embedding came from one space or the other. And the good thing about this is essentially this tries to match the two distributions as closely as possible so that the discriminator is not able to discriminate between the two. And this makes it possible to essentially, even without any aligned data between them, match the embeddings to some extent. This can also be further refined through a process called iterative refinement, where you find the closest words between the two embedded spaces and further do supervised training to try to align the two distributions. And this combination of an adversarial loss and supervised training can result in good overall accuracy in the end. This can further be applied to unsupervised machine translation, where with a cycle consistency loss and an adversarial loss. And basically the way it works is you have a cycle consistency loss where you start with a target sentence, you convert it into a source sentence, and then you have a loss with respect to the conditional probability of the target sentence given this generated source sentence. So basically what this is saying is we convert the target to the source to the target, and we want to compare the similarity between the sentences in this round trip direction. And so this will encourage the model to generate outputs that are similar to the original target, but at the same time we would like the source sentence to be in the same style as the target sentence. So in order to encourage the style to be similar, we have this adversarial loss that tries to get things that are in the source and the target to be essentially similar distributions. So I'm not going to go into this a whole lot. There's a lot to talk about, unsupervised methods for style transfer, supervision, translation, but that's the basic idea here. And finally, I'd like to talk a little bit about adversarial robustness. So the basic idea is that neural models are very sensitive to small perturbations of the input. So for example, if we add a bit of noise to the input of a translation system, a human could read it and be insensitive to this noise. But a machine translation system, the accuracy would go way down as you change more tokens in the source sentence. And in particular, adversarial noise is noise that's specifically designed to break systems. So what you do is you essentially calculate a gradient back into the input to try to reduce the probability of getting the correct label. And you can show that even with very small changes to the input, image or something like this, you can change a cat into an airplane or some other, or the classification of cat into some other class like airplane or something like this, despite the fact that these perturbations of the input are basically invisible to the human eye. However, for text, it's a little bit more difficult to do perturbations because text is a discrete format. So if you change it, it's visible to the human eye. But for example, in this source, we have Augusta being the a word in the source, but if you add just a few letters to this word, it changes Augustine to Rutgers, so it completely changes the meaning of the output. And here, if we add one little typo here, the adversarial output becomes a psychopath instead of psychotherapist. So this is an example of kind of an adversarial perturbation where we only change a few characters of the input, but nonetheless it changes the output greatly. So how do we define an adversarial example? And basically, for example, sequence generation tasks or classification tasks, basically we believe it should be meaning preserving on the source side and meaning destroying on the target side. So the meaning on the source side basically remains unchanged. The meaning on the target side should be completely changed. So if it's text classification, you should change the label into another unrelated label. If it's text generation, you should change the generated text into a different variety of text. So if we have a similarity score between texts, so we have the original text and the modified text, we could have the original similarity between the source and the target, and so we say the source meaning destruction is 1 minus the similarity of the source here, and then the target meaning destruction is this d target, and we can define basically the similarity of the target divided by the overall similarity of the target in the original output according to the sequence system, for example, if we're doing text generation. And this similarity could be defined using a semantic similarity measure or something else. But I think the most important thing is when we're talking about an adversarial example, particularly for text, let's say we flip only one word in the sentence. Both this input here and this output here are only flipping one word, but the big difference is that the simple misspelling, you can still recover the original meaning of the sentence, but this flip of the word to an entirely different word basically destroys the main meaning of the sentence, and it's also a very important word because it's a proper name. So I think this framework here provides a good way to think about adversarial examples for text. So finally, I'd like to mention adversarial training, and basically we'd like to train our models to be robust to attacks, especially in high-stakes settings. So for example, let's say we're building a spam filter. Spammers would like to replace one letter in their input and fool our model. So we'd like to train our models to be robust to this. So there's a very simple idea where basically we sample adversarial examples at training time and make sure that they're also classified correctly. Basically we can demonstrate that this is kind of an ideal method of adversarial training. So just sample examples according to whatever we classify as an adversarial example, any meaning preserving on the source side, but meaning destroying on the target side example. And there's lots of theory about this, particularly in the image domain, but little for NLP tasks. But anyway, I highly recommend this adversarial machine learning tutorial if you're interested in learning a little bit more about this. So that's all I have for today. I talked about a whole bunch of different adversarial objectives, and I think we can have a brainstorming session in the class to discuss a little bit more about these methods and how they can be applied to interesting problems for you, where you want to either generate realistic looking outputs, distinguish between features, or prevent adversarial attacks on your models from having bad consequences. So thank you very much, and that's all I have for today.